On that topic, let's go to number 3. Explore. Best practice number 3, explore. We had a customer come to us on some sort of super secret government project. They wanted to put some sort of missile or something at Mach 4 and analyze the flow around it, and it was going to do some sort of either spying or something. We don't know. It was a super secret government project. Well, obviously we can't use that design either. So I made up this other design. It's kind of a cross between a Star Trek shuttlecraft and a ramjet that I saw in aerospace engineering college. And you can see here's an inlet for the ramjet. If you take a cross section, here's the throat that you would expect for a ramjet, and then expands for the nozzle. And I'm going to use it to illustrate what we did for this customer. He said, okay, we want to put this new design that we've never tested at Mach 4. Now, in aerospace engineering college, I did a little stuff at Mach 1 and Mach 2, but I'd never been at Mach 4. I didn't know what the numbers would be like. I didn't even have a common sense idea of what makes sense at that speed. So what I did is I put their design at Mach 1. Right? You can see a shock wave developing. Then I took their design and put it at Mach 2. And we're measuring density on these plots. You can see the ramjet is constricting like it should, compressing the air. You put it at Mach 3. Now you can really see some shock waves developing. You can see the ramjet's really constricting. It's gone past the throat. Then I said, well, let's put it at Mach 4 at ground level. And that's kind of silly. You don't really travel at Mach 4 at ground level. The air is too dense. So let's put it at Mach 4 at 25,000 feet. Well, then things started getting interesting. Then I said, well, what happens if we put it at 50,000 feet? What happens if I make the inlet a little wider? What happens if I make it narrower? What happens if I take these wings and make them a little thicker? What happens if I make them thinner? Right? So what was I doing? What happened, Al, do you think, when I met with this customer again after a week or two of doing this? Right? Who knew more about the environment?
You did.
Right. The customer knew about their product. The customer knew about the mechanics of what's going on in here. Well, because I'd done this exploration, I had a better fingertip feel for what the environment was like. He knew that the nose of the rocket would be hot. I knew how hot. He knew he'd see some density inside the ramjet. I knew how much. I knew what 50,000 feet looked like versus 25,000 feet, right? When I was in college, we only had one supersonic wind tunnel. It took about an hour to charge up, and then it would go for about 10 seconds, and you get 10 seconds of Mach 2 flow around whatever you put in the wind tunnel. There was a big, long waiting line for the wind tunnel, and you only got 10 seconds of flow. I can run these tests for hours, right? And I can put them at crazy speeds. Mach 4 at ground level, again, the thing might combust and crumple. If NASA made one of these probes and it put it out over the Pacific Ocean and it exploded, it'd be all over the headlines. It'd say, NASA spends $2 million on probe that fails. It'd be front page news. But what you can do in the virtual world is explore this product space with no consequences. You can put products in weird, unsurvivable circumstances just to see what would happen, just to learn, right? And that's what we're doing. You're free to explore without consequences. Does that make sense?
Absolutely.
All right, so that's one good way to find the blue oceans. Explore in the virtual world. As an adjunct to that, best practice 3A I'm calling it, think about exploring your heat. Over on the left-hand side, this is normal bench testing where you put thermocouples on your model. This is a guy trying to overclock his computer, and he's trying to figure out how hot his CPU gets. But where's the only place he has heat information? Is only the two places he put temperature probes. You can't put thermocouples everywhere. One, they mess up the flow that you're trying to measure, but two, they're annoying. Three, how much data can you have? When everyone thinks of simulation, especially even ours in SolidWorks, they always think of stress and strain. They always think of strength and weight and von Mises stress. But a lot of people are using our simulation to explore heat. And here's one of the models we use for our test for our class, our training class. I've put 3 different levels in here, but I can get heat anywhere in the model, right? It's not limited by how many thermocouples I have. The numbers are being calculated for every single surface in the model, right? No matter what you want to find. So especially for you high-tech electronic guys, you guys are packing hotter and hotter electronics into smaller and smaller spaces. Think about exploring your heat. Think about exploring new types of heat management. Explore them virtually before you have to build this entire test rig to figure out what's going on. One of our customers that are doing that a lot are people who do design LEDs. Philips Color Kinetics, Fusion Optics, a couple other customers. Here's a dilemma that LED designers have. Someone comes to them and says, your assembly needs to produce more light. Your LED for your car brake lights or your overhead lighting needs more light. They can have more LEDs and lower the voltage each one is using, but that's more cost. Each LED adds more cost. And if you're packing more heat sources in there, maybe you have more heat too. They can have fewer LEDs and run each one at a higher voltage. The light it puts out is proportional to the voltage, but that also generates more heat. And that means they'll definitely have a shorter life. So this one's more heat question mark, this one's more heat period. Right? So this is their dilemma. They seem like pick your poison. How do we know which is the best way to go? So what they're doing, just like we saw on the screen before, they're trying the designs out virtually. They're exploring different options. Maybe we cluster the LEDs. Maybe we spread them out. Maybe we vent them. Maybe we don't. Right? And they're figuring out how the heat goes in their models. So they're having a lot of success with that at those two companies. And one thing real quick, to show you that we have two different choices. This question comes up a lot, so I figured I'd throw it in there. If you're mainly doing conduction, this is more for the working level engineers. If you're mainly doing conduction, and you've got some assumed coefficients for convection, radiation, examples of this would be an iPhone. There's not a lot of convection going on inside an iPhone. It's packed so tightly. If you've got an oven and there's no airflow in the oven, you just want to see how fast your potato cooks, right? No convection. You can use our Simulation Professional package. It's got a thermal module. We have some customers doing that. But if you want to do a full-fledged three-source, conduction, convection, radiation test, you want to see where all the heat's going, all the different modes of heat transfer, you should use flow simulation. Right? That's the example I just showed before. That's what most of our customers are doing. But again, you have to decide. We'll help you decide when you're talking to us. But that's the difference between the two modes. We get that question a lot. All right, that's best practice number 3. We're about halfway through. What's the time look like, Al? Okay, all right, we're right on schedule then. All right, so we've talked about exploring, exploring different project space, exploring different ideas to try and find that blue ocean.